So in this video, I'm going to discuss overfitting, which is a issue that we're confronted with constantly when we train machine learning models. Overfitting. Basically, the issue is sometimes our model can appear to be doing very well on the training data, but then it might do much worse on the test data. And this is something we have to always be on guard against. So to introduce the idea of overfitting, I'm going to first review our setup for a logistic regression for binary classification. So suppose for simplicity and for the purpose to make it easier to visualize, suppose that the feature vectors are points in R2. And how does logistic regression work? If these are the components of the ith feature vector, then the way we compute our predicted probability, as we know, is we compute this quantity, beta naught plus beta 1 times the first component of xi plus beta 2 times the second component of xi. We take that number, we plug it into the sigmoid function. As we know, the sigmoid function is useful because it converts a number into a probability, and that's our predicted probability. If this number, if this predicted probability is greater than 1/2, then we predict that the label for the ith training example is 1, and otherwise we predict the label for the ith training example is 0. These three numbers, beta naught, beta 1, and beta 2, these numbers are like knobs in our model. These are knobs that we can tune to make our predicted probabilities as accurate as possible. And if our predicted probability is greater than 1/2, we predict that the class is 1. Otherwise, we predict that the ith training example belongs to class 0. Now, to say that this predicted probability is greater than 1/2, that's equivalent to saying that this quantity here is greater than 0. Those two things are equivalent. For this to be greater than 1/2 is equivalent to saying that this is greater than 0. So another way to describe our classification rule is if this quantity is greater than 0, we predict the class is 1, otherwise we predict the class is 0. Now, what if this quantity turns out to be exactly equal to 0? Then we don't know what to do. That would mean that our point xi lies on the decision boundary. The decision boundary consists of all the points where this quantity here is exactly equal to 0. That means we don't know if we should predict positive. We don't know if we should predict the class is 1 or 0. This quantity is exactly 0. This is the decision boundary. And this decision boundary, if you graph it, is a line. So when we do logistic regression, we're using a linear model and the decision boundary is a line. And we've seen that before. We've plotted that line in some of our homework and some of our projects. Now, what if we're not using a linear model? What if instead of doing logistic regression, we're training like a neural network or something? So instead of having this function, which I'll call f sub beta of xi, instead of having this function be a linear function or an affine function, which is what we do in logistic regression, this function f sub beta could instead be a neural network. Could be a non-linear function, such as a neural network. It could be a neural network that has many parameters, many layers, and in that case, where f beta is a more complicated nonlinear function with many, many parameters, if it's a neural network, it could have millions of parameters. In that case, this function has a lot more flexibility. We have many more knobs that we can tune. We have many more knobs that we can tune. If we have a neural network with many layers and like a million parameters, all those parameters are knobs we can tune. And as a result, this function in that case has a lot of flexibility. And if you train your neural network and then plot the decision boundary, that decision boundary isn't going to look like a line. It's going to be some curve. The decision boundary is not going to be a line like this. This is what happens in logistic regression. When our model is nonlinear, the decision boundary is going to be some kind of curve like this, or even something crazy looking like this. Now, if we look at this curve here, that seems pretty good. This curve is doing a good job of finding a nice boundary between the positive examples and the negative examples. It looks like this curve is probably a better decision boundary than this one over here. And I would expect that when we try out this classifier, when we try out this model on the training data, on the test data, we're going to have good accuracy. On the other hand, this decision boundary looks bad because this decision boundary is doing crazy things which are only helpful on the training data set. The things that this decision boundary is doing, that's not going to be helpful on the test data set, which the model has never seen before. This decision boundary is taking advantage of quirks that exist only in the training data set. And when this model is faced with new data that it's never seen before, these things it's doing is not going to be helpful in that case when it's faced with new data. This model is bending over backwards to do as well as possible on the training data, but that is not going to help it do well on the test data. In fact, it's going to make it do worse. So this model, this is an example of overfitting. Whereas this is what we want, but this is overfitting. And this can happen when our model is very flexible, when it's like a neural network with a lot of parameters, for example, many knobs that we can tune. Our model is very flexible and it can do things like this. And so we have to be very careful to avoid this situation. We don't want our model to overfit the training data. And this is an issue that we constantly are confronted with when we're training machine learning models. So now I want to observe overfitting in a real example. And the example we're going to use is classifying IMDB movie reviews as either positive or negative. Is it a favorable review? Did they like the movie? Or is it an unfavorable review? Did they dislike the movie? We're going to train a neural network to classify IMDB movie reviews. And in the process, we're going to observe overfitting. So this code that I'm going to show you, this is based closely on chapter 3 of the book Deep Learning with Python by Francois Chollet. It's a great book, one of my favorite machine learning books. I recommend it highly. So let's take a look at this code and see what we're doing. So we're going to import TensorFlow, and this line here just reads in the IMDB data. So let's execute this section of code. We're reading in the IMDB data right now. Takes a minute. Okay, and let's see what we've got. We've got something called train data. And it is just a NumPy array. And it has 25,000 entries. And let's look at the first entry. Each entry is a list of numbers. So if we do type of train data of 0, it's a list of numbers. And let's look at the length of the first training example, 218 numbers. And these 218 integers encode a movie review. And here's a little snippet of code which can be used to decode the movie review so we can actually read it if we want to, just to get more familiar with the data. So I'm going to run this section of code and we're going to compute this decoded movie review. We're taking the first training example here and we're decoding it to get this decoded review. Okay. So let's see what we've got. We've got this thing, decoded review. It's a string. Let's print it out. Okay, now we can actually read this. This film was just brilliant. Casting, location, scenery, story, direction. Everyone's really suited to the part they played. You could just imagine being there. So this is an example of a movie review. This is a positive review. I mean, as a human, I can classify this review as positive. We're trying to train a neural network to do that. So that's the data that we're working with. So, and let's look at, what does this number 10,000 mean? That means that in all the training data, in all the movie reviews that appear in our training data, we're only gonna keep the 10,000 most popular words, and the other less popular words are just gonna be omitted from the training data. We're only gonna keep the 10,000 most popular words. So let's look at, like, let's see that. If I do max of, and then the list of all, max of S for S in train data, then the maximum value is 9,999. So that reflects the fact that we have kept only 10,000 words. So each of these movie reviews is a list of words, and there's only 10,000 possible words. And each of those words has been encoded as an integer between 0 and 9,999. So let's look again at train data of 0, our first movie review, and let's look at the first 10 words. Okay, so we have these, you see it's a list of integers, but each of these integers corresponds to a word. And if we want to decode the review, we can do that using this snippet of code. So that's the data that we're working with. And let's look at train labels. It's a NumPy array. And then let's just look at the first label. It's a 1. Let's look at the first 5 labels. 1, 0, 0, 1, 0. So you can see each training example, each movie review in the training data set has been labeled. 1 means favorable, 0 means unfavorable. And you can tell when you read this movie review that this is a favorable review. That's why the first label is 1. Let's look at the second. Let's decode the second review. And let's read that one. So decoded review. That's a negative review. Let's look at the third movie review. Decoded review. This has to be one of the worst films of the 1990s. When my friends and I were watching this film, okay, so that's a very negative review. And correspondingly, if we look at the train label for this movie, it's 0, meaning it's a negative review. So that's our data. We have looked at the data. We know what we're working with. Now, here's an important question. If we're going to train a neural network to classify these movie reviews, then every movie review has to be encoded as a vector. Every movie review has to be represented as a vector. But a movie review, as it stands right now, is just a list of words. And these lists don't all have the same length. Like if we do, let's look at the length of the first movie review. The length of the first review, it has 218 words. The second review has 189 words. The third review has 141 words. How do we represent each review by a vector in RD? Here's what we're going to do. You know how there's 10,000 words in our dictionary? Each movie review is going to be represented by a vector with 10,000 components. And each of those components is going to be either 0 or 1. And the first component is going to be 1 if the first word in the dictionary appears in the movie review. Otherwise, the first component of this feature vector is going to be 0. The ith component of this feature vector is going to be set equal to 1 if the ith word in the dictionary appears in the movie review. Otherwise, the ith component of our feature vector is going to be set equal to 0. That's how we're going to construct feature vectors that's how we'll construct a feature vector that describes a movie review. And that's what this section of code is doing. We have this function called vectorize reviews. It takes a list of movie reviews as input. So for example, it takes train data as input, and it creates an array, a NumPy array, where each row of this NumPy array is going to be a feature vector that describes a movie review. And you can see that what's happening here is that all the components of this ith feature vector that correspond to words that appear in the review, all those components are being set equal to 1. That's how we're constructing our feature vector. So let's run this section of code. Takes a second. And now let's look at what we've got. If I do x.shape, oh, sorry, let's do xtrain.shape. Okay, 25,000 rows. That's because our data set, our training data set, consists of 25,000 movie reviews from IMDB. And each vector, each feature vector has 10,000 components because our dictionary has 10,000 words in it. And let's look at xtrain. Let's look at the first feature vector. So I'll do xi equals xtrain of 0. Now we're looking at our first feature vector, xi.shape. It's a feature vector with 10,000 components. And let's look at the first 20 components. Okay, so you can see each component of this feature vector just tells you whether or not the corresponding word in the dictionary appears in this movie review. So now we have feature vectors. That's good. Okay, we want to make sure that our label vectors are stored as floats instead of ints. So that's what these two lines of code do. And let's look at ytrain. So we have 25,000 labels. That's all ytrain is. Let's look at the first 5 labels. There we go. Okay. Now we come to an important point where we have to decide on the architecture for our neural network. And that's what we're going to specify here. When I say that we have to decide on the architecture of our neural network, I mean we have to decide things like how many layers will our neural network have? How many nodes will there be in each layer of the neural network? And here's the architecture that we're going to use in this example. So we're going to have a neural network. We're going to create a neural network that has 1 input layer, 2 hidden layers, and then an output layer. And you can see here we have all the components of our feature vector xi. They're fed into the input layer. And then I mentioned before, each of these nodes in the neural network you can think of as being a little computational unit that performs its own little computation. So what this node here does is it takes the input vector xi, it computes the dot product of xi against the weight vector that this node, that belongs to this node, then it adds the bias term that belongs to this node, and the result of that computation is plugged into the ReLU activation function, and the output is a scalar, which is then fed in as input to each node in the next layer of the network. And that's what That's the computation that each of these nodes performs. Each node has its own weight vector and its own bias term, and each node performs a dot product with the input vector, adds the bias term, plugs into the ReLU activation function, and then the result of that computation is passed on as input to each node in the next layer of the neural network. That's how it works. And I haven't drawn all the connections between these nodes, but because it would be too messy, but this is a dense neural network, fully connected. So the output of this node is fed as input to each of the nodes in the next hidden layer. The output of each of these nodes in the second hidden layer, each of these outputs is fed as input into this final node, which is the single node in the output layer. This node in the output layer, it takes all the inputs from the previous layer, store it as a vector, it computes a dot product with the weight vector which belongs to this output node, it adds the bias term that belongs to this output node, and then the result of that computation is plugged in not to the ReLU function this time, but plugged into the sigmoid function. And that's to convert it into a probability. That gives us a number between 0 and 1, which can be interpreted as a probability. So this final unit, this final node, it does not use the ReLU activation function. Instead, it uses the sigmoid function in order so that the output can be interpreted as a probability. And that probability tells us how to classify the input vector xi. Now let's count up how many parameters are there in our neural network. Well, the input vector is a list of 10,000 numbers. This first node here is going to compute a dot product against that input vector. That means that the weight vector for this node has to be a vector with 10,000 components. And then this node also has a bias term. So the number of parameters that belong to this particular node is 10,001 parameters for this single node. And it's the same number of parameters for all of these nodes. And in this neural network, we have 16 nodes in the first hidden layer. So the total number of parameters for this hidden layer is 10,001 multiplied by 16. That's for the first hidden layer. Now, let's count how many parameters are there in the second hidden layer. How many parameters are there for this node right here? This node is going to take all the outputs from the previous layer. That's a vector with 16 components, and it's going to compute a dot product against that vector, which comes from the previous layer. That means that the weight vector for this node has to have 16 components. This node also has its own bias term. That means there are 17 parameters that belong to this node alone. So, and it's the same thing for each node in this hidden layer. And the number of nodes in this hidden layer is 16. So the number of parameters in this hidden layer is 17 times 16. Okay. Now, how many parameters are there for this final node, the output node? Well, this node is going to take the output from the previous layer as its input vector. That's a list of 16 numbers. It's going to compute a dot product against that vector. That means that the weight vector for this node has to have 16 components. This node also has its own bias term. So that is 17 components for this node. So the total number of parameters for our neural network is 10,001 times 16 plus 17 times 16 plus 17. That's how many parameters there are in our neural network. Each of those parameters is a knob that we can tune to increase the accuracy of our neural network, increase the accuracy of our predicted probabilities. But keep in mind, because we have so many knobs we can tune, that means that this neural network is very flexible. And if we allow it to, it will bend over backwards to satisfy the training data. It will do, the decision boundary will be crazy if we allow it to be crazy. So we have to be on guard against that because this neural network is so flexible. So now here's the point in the code when we are creating our neural network. And these lines of code where we're creating our model, this corresponds exactly to the picture we were just looking at. So there's going to be the first hidden layer that has 16 nodes. The input to the first hidden layer has 10,000, we have 10,000 inputs. And each node in the first hidden layer is going to use the ReLU activation function. Now we're defining here the second hidden layer, which also is going to have 16 nodes. Each node in the second hidden layer is also going to use ReLU. And then we're defining here the final output layer, which has only one node. This node uses the sigmoid function. Instead of ReLU, it uses sigmoid, just as we discussed. So this line of code, this section of code creates our model, and then we have to do this compilation step where we compile our model. And when we compile our model, we tell TensorFlow which optimization algorithm to use. Now, we have discussed stochastic gradient descent, in other words, also known as SGD. Here, we're going to use a fancier optimization algorithm called RMS-prop. RMS-prop is very popular when training neural networks. It is similar to SGD. It's similar in spirit, but it's a little fancier. It has a few bells and whistles that on top of SGD. Maybe it has an adaptive way of choosing the step sizes. It could use momentum. So there's various optimization algorithms that are popular when training neural networks. RMS-prop is one of them. There's another algorithm called ADAM that's popular. They're all similar in spirit to stochastic gradient descent. So if you know stochastic gradient descent, you know the main idea. We're going to use RMS-prop in this case. The loss function is just like when we do logistic regression for binary classification, we use the cross-entropy loss function to compare our predicted probabilities with the ground truth probabilities. We're doing the same thing here. That's our loss function. And we're going to have it, we're going to tell TensorFlow to keep track of the classification accuracy as it trains the neural network. Okay. Now, in order to guard against overfitting, we have to take our training data and break it up into two pieces. One of them is going to be the collection of training data that we use to actually, one of them is going to be the collection of data that we use to actually train our neural network. And then there has to be a separate data set, which is called the validation data set. And after we train our neural network, we're going to try it out on the validation set, and we're going to see how did it do. And we're going to compare. Does our neural network do much better on the training data than it does on the validation data? That's a sign that we have, well, that always happens a little bit, but if that happens a whole lot, it's a sign that we have overfitting going on. And so that's what we're doing in this section of code here. We're dividing the training data into two sets. The validation data set, which is going to have 5,000 examples, and then the data that we're actually going to train our neural network on, which is going to have 20,000 examples. So let's look at partial x train.shape, 20,000 examples that we're going to use. Okay. And then keep in mind we also have a third collection of data, which is called X-test. And X-test is a set of data that we're not going to touch until the very end, until we're not going to touch X-test. We're not going to look at X-test until we have already finished training our model. We've already decided on the best architecture. We've already decided on the best hyperparameters. We think we're in good shape. Now we need to finally demonstrate that our model performs well on data that it has never seen before. So we're at the very end, we will try our model on X-test, but that's on the test data set. That's something we only do like right before we put our model into production, or it's something we only do like, you know, a few days or a week before we publish our paper about our neural network algorithm that we're developing. So all of our data has been broken into 3 pieces. We've got the test set, which is not touched until the very last moment. We've got the validation set, and we've got the data that we actually use, the training data that we actually use to train our model. And a typical process is you typically train your model on the training data. You see how it did on the validation data, and then you say, oh, it overfits, so we need to use fewer epochs, or we need to use regularization, or we need to use a different architecture. And so you tweak your hyperparameters, you train again on the training data, you check how you did on the validation data. There's this little loop here where you modify your hyperparameters, you retrain on the training data, check on the validation data. You go through that loop, that cycle several times. Then when you finally think your model is ready to go, then you finally check that it still works well on the test data, which it has never seen and never touched. And if it does well on the test data, then you're ready to release your model into production. So we have what we have now is we have our validation data set, and we have our data set here, which we're currently calling partial X train and partial Y train. That's the data we're going to use to actually train our model. Okay, now here's the step where we are ready to actually train our neural network. That's what we do in this line of code here. And we're telling TensorFlow to use 20 epochs. And you remember I discussed in stochastic gradient descent, we don't have to use a batch size of 1. We can use other batch sizes. In this case, we're using a batch size of 512. And then we're giving TensorFlow, we're telling TensorFlow to keep track of how well we're doing on the validation data as the training progresses. So let's go ahead and train our model. And you can see here we're on epoch 1. It reports on the accuracy that we're getting. So we're looking at 87 on validation accuracy right now of 87%. Okay, we just did 20 epochs and we have trained our model. And now we're ready to look at the results. So this history variable contains a lot of useful information about various metrics that were recorded during the training. And here we're extracting a Python dictionary, which is part of the information stored in this history variable. And then what this variable loss values tells us is the objective function value at each iteration of stochastic gradient descent, or at each iteration of RMS prop. And that's the objective function value as measured on the training data set, which is the data we're using to train our model. And then this variable here contains the objective function value at each epoch of stochastic gradient descent. But this is the objective function value as measured on the validation data set. This is the validation data that we're not looking at as we train our model. Okay, and this code here just makes a plot of these two quantities. So let's see what we've got. So here you can see The dotted curve, that's our objective function value at each epoch, measured, computed using the training data. This solid curve, that's our objective function value at each epoch computed using the validation data. And you can, here we see overfitting happening. We are face to face with overfitting. So for the first couple epochs, we're making progress on both the training data set and the validation data set. But starting at this point, we continue to make progress on the training data, but we start actually doing worse on the validation data set. That means that we are overfitting. We observe the validation loss is getting worse while the training loss is getting better. That's overfitting. The model is too flexible. The model is it's bending over backwards to do well on the training data set, which is what it can see, but the things it's doing are not helpful on the validation data, which it has not seen. That's overfitting. And let's also look at our classification accuracy. So here we have the classification accuracy on the training data set, which the model sees during training. Here we have the classification on the validation data set, which the model does not see. Let's plot those two things. And you can see the training accuracy on the training data set continues to improve all the way up to almost 100% on the training data set. But after this point here, the accuracy on the validation data set is no longer improving, and it's actually like maybe getting a little bit worse. So at this point, the model it's doing better on the training data, but it's doing like a little bit worse on the validation data. This is overfitting, and this is what we want to avoid. So the simplest way to avoid overfitting in this case is let's just stop after 4 epochs. Like right around here, let's just stop after a few epochs. So now I'm just gonna clear my variables and just train the neural network again, but this time I'm gonna use just 4 epochs to train it instead of 20 epochs. So let's just see how this does. The easiest way to guard against overfitting is just to stop early. Instead of using 20 epochs, maybe just use 4 epochs. Just look at your plot of the validation error versus the training error, and you can, by looking at that plot, you can decide how many epochs of gradient descent of stochastic gradient descent should you use before you start to overfit. So here we did 4 epochs, and now let's finally check and see how does our model do on the test data? This command just checks how well our model performs on the test data, which our model has not seen yet. Takes a second to evaluate. So we'll discuss other fancier versions of regularization. The simplest type of regularization is just early stopping. That's what we did here. It's the easiest way to guard against overfitting. Okay, so it looks like we have 88% accuracy on the test data. So we have trained a neural network to classify IMDB movie reviews, and we have 88% accuracy. And state of the art is about 95%, so it's not too bad. So I mentioned that we've been taking this example with the IMDB data set from chapter 3 of the book Deep Learning with Python by Francois Chollet. He's the creator of Keras, and he's one of the best machine learning researchers, and he explains things really clearly. So I recommend his book highly. Here are some further experiments you can try using the IMDB example. Try changing the number of hidden layers. So try 1 hidden layer or 3 hidden layers. how does this affect your accuracy on the validation set? And you could try using, instead of 16 nodes in the hidden layers, try using 32 nodes or 64 nodes. Instead of using the binary cross entropy loss function, try using mean squared error instead. That's not what you're supposed to do. For a binary classification problem, you're supposed to use binary cross entropy. Mean squared error is used for regression problems, but it would be interesting to try it in this example and just see what happens. Also, we've been using the ReLU activation function mainly, but it's not the only activation function. There's a classic activation function, the hyperbolic tangent activation function. You can try that one and see how that works. Probably you get better results with ReLU, but it'll be interesting to see what happens. And here are some lessons, some takeaways from this example. So often quite a bit of work goes into pre-processing the data before it's in a form that you can feed into your neural network. And another lesson is that just neural networks consisting of several dense layers using ReLU activation functions that tend to be useful. And here's something important to understand. If you're doing a binary classification problem, then your network should end with a dense layer that has one unit and which uses the sigmoid activation function. And as we've discussed, the reason we use the sigmoid activation function is because it outputs a number between 0 and 1, which can be interpreted as a probability. And that's what we want when we're doing binary classification. Another observation is that the optimization algorithm we use, which is called RMS prop, tends to work well. Here's a really key point. As your training progresses, as your neural network training progresses, you have to monitor your performance on a validation set in order to see if you have begun overfitting the training data.